When we gaze up into the night sky, the sparkling stars and faint nebulae we see are just the beginning of a much vaster picture. The idea of the universe as an infinite expanse is deeply ingrained in our imagination. Yet scientifically, we know there are boundaries to what we can observe from our vantage point here on Earth. This leads us to contemplate a fundamental question. How far can we see within the cosmos? This boundary, known as the observable universe, defines the limits of our cosmic vision and shapes much of modern cosmology. The universe, as vast as it is, did not always exist in its current form. It began with the Big Bang approximately 13.8 billion years ago, an event that marked the birth of space, time, and all energy and matter. Because the universe is not infinitely old, light from very distant regions has only had a limited amount of time to reach us. In essence, the observable universe is bounded by a cosmic horizon, the maximum distance from which light has traveled to Earth since the dawn of time. This boundary is not simply fixed by the age of the universe multiplied by the speed of light. While light does travel at the ultimate speed limit of approximately 299,792 kilometers per second, cosmic expansion plays a crucial role in defining the observable limits. The universe itself is expanding, a phenomenon discovered through the redshift of distant galaxies, which means that regions of space are receding from us, sometimes at speeds that effectively exceed the speed of light due to the expansion of space itself. This expansion means that the farthest objects we can observe are not just 13.8 billion light-years away. Instead, the radius of the observable universe extends to about 46 billion light-years in every direction. This larger scale arises because the universe has been expanding continuously throughout cosmic history. Visualizing this, imagine the universe as a balloon being inflated. Objects on the balloon's surface move apart as the balloon grows, much like galaxies between which space stretches. Even though the light from some distant galaxies started traveling towards us long ago, the space in between has expanded, causing those galaxies to be much farther away now than the distance light has traveled. Therefore, the observable universe encloses a sphere roughly 93 billion light-years in diameter, containing everything from the nearest stars to the farthest detectable sources of light. The observable universe holds within it a staggering number of galaxies, on the order of 2 trillion according to recent estimates, and each galaxy contains billions or even trillions of stars. The sheer scale challenges human comprehension, yet technology has enabled scientists to peer ever deeper into space and, concomitantly, further back in time. Telescopes like the Hubble Space Telescope have allowed astronomers to observe galaxies as they appeared billions of years ago, shortly after their formation. The images captured are not just pictures of distant objects. They are snapshots of ancient light traveling through the cosmos over unimaginable expanses of time. However, there is a subtle but profound distinction between the observable universe and the whole universe. The term observable universe refers only to that portion of the entire cosmos from which light or other signals have had time to reach us since the Big Bang. Beyond this lies the unobservable, inaccessible region of space where events are occurring, but their information cannot yet be detected. It is conceivable, according to many cosmological models, that the universe itself extends vastly beyond what we can see, possibly infinitely. Yet those regions lie forever hidden behind the cosmic horizon, beyond the scope of direct observation. An analogy often used to describe this concept involves standing in a vast desert at dawn. The light you see is from the sun that has risen and illuminated the visible surroundings. But there remain regions hidden in the distance behind hills or sand dunes, areas you cannot see directly because of obstacles and limits in your line of sight. The observable universe is akin to this region illuminated by the cosmic sunshine of the Big Bang, while the rest of the universe beyond the horizon remains shrouded in darkness. To understand how we set the limits of this horizon, it is helpful to delve into how the speed of light fundamentally constrains our observations. No signal or influence can travel faster than light in vacuum, according to Einstein's theory of relativity. This universal speed limit ensures that information from beyond a certain distance, one that grows with time since the Big Bang but is finite at any given moment, cannot reach us yet. In other words, events occurring too far away have not had sufficient time for their light to arrive on Earth, hence cannot be observed. This cosmic limit is dynamic. As time passes, the horizon expands, revealing new regions of the cosmos previously hidden. The photons from farther distances take progressively longer to reach us, and so with advanced technologies and patient observation, we incrementally push the boundary of what is observable. Yet, because of the accelerated expansion caused by dark energy, the farther reaches of the universe may eventually move beyond our observational horizon, retreating faster than light signals can close the gap. Thus, the observable universe represents a continuously evolving sphere, a window into the past, delimited by the laws of physics, the age of the cosmos, and the stretching fabric of space itself. It invites us to explore the limits of knowledge and the nature of reality beyond what is immediately perceivable. Peering into this vast observable cosmos reveals an intricate web of galaxies, cosmic filaments, dark matter, and dark energy. These components weave together the large-scale structure of the universe, and each observation uncovers clues about its origin, evolution, and fate. The observable universe is a rich archive of cosmic history, containing the relic light emitted shortly after the Big Bang, radiation now observed as the cosmic microwave background, the formation of the earliest galaxies, and the emergence of complex structures over billions of years. This exploration also challenges our terrestrial perspective. We are not located at any special point in the universe. The observable horizon extends equally in all directions, defining a sphere centered on Earth simply because that is our observational standpoint. If an observer elsewhere in the cosmos could also measure their observable universe, their view would encompass a similar size sphere centered upon their position, overlapping yet distinct from ours. Considering how far we can see raises profound questions about the universe's size, shape, and nature. Does the universe wrap around itself, such as in a closed geometry? Or does it extend infinitely in all directions? While the observable universe is finite and bounded, the broader cosmos might not be, and unraveling that mystery is a major goal of cosmological research. In focusing on the observable universe, we are simultaneously peering into the depths of space and time. Every glimpse forward in distance is a glimpse backward in time, because light travels at a steady speed, and the farther away an object is, the longer its light has taken to reach us. Observations from the furthest reaches hence inform us about the early universe, the conditions during the formation of the first stars, galaxies, and ultimately the seeds of cosmic structure. Summarizing, the observable universe is a tangible yet vast concept, a cosmic horizon defined by the finite age of the universe, the immutable speed of light, and the dynamics of cosmic expansion. It shapes what we can know, framing the grand cosmic story within the limits of physics and time. Yet it also invites us to ponder what lies beyond, and how our view might evolve with time and technology. As we conclude this initial step into understanding cosmic limits, the next logical journey is to better define this cosmic horizon itself, the boundary that marks the ultimate edge of observation, a threshold beyond which light has yet to reach us. This boundary, known as the cosmic horizon, offers a fascinating doorway into the universe's structure, evolution, and vast mysteries that continue to inspire the human quest for knowledge. Continuing from our exploration of the observable universe, we now turn our attention to the cosmic horizon, a fundamental concept that defines the absolute edge of what we can perceive or detect across the expanse of space and time. The cosmic horizon is not simply a boundary in space, but also a limit set by the universe's history, its expansion, and the immutable speed of light. Understanding the cosmic horizon illuminates the profound structures that encapsulate our observational limits and shapes how we envision the cosmos itself. To begin, it is essential to recognize that the cosmic horizon is a consequence of the finite age of the universe, combined with the finite speed at which information travels, namely, the speed of light. Since the Big Bang occurred about 13.8 billion years ago, any signals or photons emitted from regions farther away than light could have traveled since that time have not yet reached us. However, because the universe is undergoing expansion and space itself stretches between objects, the distance to the farthest observable objects today is much larger than a simple multiplication of the speed of light by the universe's age. This interplay results in a complex and dynamic cosmic horizon. There are a few ways to conceptualize this horizon, but one of the most intuitive is to think of it as the spherical boundary that encloses all points in space from which we have received light since the beginning of the cosmos. This radius, currently about 46 billion light-years, defines the observable universe's physical size. Beyond this boundary lies the unobservable realm, regions so distant that either their light has not had the time to reach us, or cosmic expansion prevents their signals from ever arriving. Importantly, the cosmic horizon differs from what we might colloquially call an event horizon, like those found around black holes. While an event horizon is a local boundary marking a point of no return for matter and information falling into a black hole, the cosmic horizon operates on the largest scales imaginable. It marks the limit beyond which events can have no causal influence on us at the present time, because their emitted light or signals cannot have traveled fast enough to arrive. This means that the cosmic horizon is essentially a causal horizon, dictating what portions of the universe could have had any kind of interaction or communication with our region of space. Physicists often refer to this concept as the particle horizon or the cosmological horizon. The particle horizon sets a boundary in past time and space beyond which no particles or waves of any information could have reached an observer. It represents the maximum distance from which particles could have traveled since the time of the Big Bang. This horizon is distinct from the event horizon associated with the universe's accelerated expansion, which defines the boundary beyond which signals emitted now will never reach us in the future due to the continuing acceleration caused by dark energy. To grasp this better, consider how the cosmic horizon evolves. Early in the universe's history, the horizon was much smaller. Photons and particles emitted even slightly beyond the horizon were forever unreachable then, and remain so until the horizon expands sufficiently to incorporate them. As time moves forward, this boundary enlarges, revealing more of the universe's vastness. However, due to dark energy causing accelerated expansion, some regions that are currently within our horizon may eventually recede beyond what's called the event horizon, meaning any light emitted from them now will never reach us. This dynamic interplay between expansion and information flow makes the cosmic horizon a moving boundary, evolving as the cosmos ages. Why is this significant? The cosmic horizon delimits not only what we can observe, but also what we can, in principle, ever know about the universe. This ties our understanding deeply to the physics governing light, space, and time, and constrains cosmology's scope. It means that portions of the universe, even if they exist beyond doubt, can remain unknowable, hidden behind an ever-present veil. An analogy might help clarify this. Imagine you are on a vast shoreline, looking out over a continuously foggy sea. Your vision is limited by the fog and light. It cuts off at some distance, where the world beyond the mist remains invisible regardless of your efforts. The cosmic horizon acts like that fog line, a natural limit set by physical laws, beyond which no observation or signal can penetrate at the current epoch. This cosmic fog represents a fundamental boundary, but it's not static or uniform. The expansion rate of the universe influences how quickly the horizon changes. For example, prior to the discovery of the universe's accelerating expansion in the late 1990s, scientists considered a universe that might slow its expansion over time or even contract, potentially altering the horizon's limits drastically. With dark energy entering the equation, the horizon began to behave differently, in some ways stabilizing the size of the portion of space that will remain visible, while constantly pushing other regions beyond reach. In addition to the particle horizon, cosmologists also discuss the event horizon related closely to our cosmic fate. The event horizon defines the maximum region we will ever be able to observe. Any signals emitted now from beyond this boundary won't ever reach Earth, no matter how long we wait. This creates a future observational boundary beyond which regions of space, though possibly within our current horizon, will eventually become causally disconnected. Mathematically, these horizons can be described using models from general relativity and the Friedmann-Lemaitre-Robertson-Walker (FLRW) metric, which reflects the large-scale structure and dynamics of the universe. Using these tools, cosmologists can calculate the limits of what we can observe and predict how those limits evolve with cosmic time. The precise values depend on parameters such as the Hubble constant, the density of matter and dark energy, and the curvature of space. This physical framework profoundly influences how we interpret the light arriving from distant galaxies and the cosmic microwave background, the radiation left over from the early universe's hot, dense state. The cosmic horizon effectively determines the oldest and most distant signals we can detect, setting the stage for studying the universe's infancy and its subsequent evolution. Moreover, the concept of the cosmic horizon challenges some intuitive notions. Because space itself is expanding, distant objects can recede from us at speeds exceeding the speed of light, not because they travel through space faster than light, but because the fabric of space between us stretches. This counterintuitive fact means objects currently beyond the cosmic horizon might never be reachable or observed, even though they exist. This intrinsic limit imposed by the cosmic horizon fosters deep philosophical questions about the nature of reality and our role as observers. It reminds us that our perception of the universe is fundamentally limited and filtered through cosmic history and expansion. Everything we know about the universe derives from signals within the horizon. Beyond that lies a realm unknown and potentially unknowable. In the next part of this journey, exploring light, time, and distance, we will investigate how these cosmic signals carry information across these vast limits, how their travel time and properties shape our understanding, and how we interpret the messages sent across billions of years and light years. Such insights will deepen our grasp of the cosmos and sharpen the notion of observation constrained by horizons. For now, the cosmic horizon remains a breathtaking reminder of the universe's grandeur and the subtle yet firm limits set by nature on what and how much we can perceive. It defines the edge of our cosmic stage, a frontier spanning space and time that we continually strive to explore, understand, and respect. As we embark further into our cosmic journey, it becomes essential to understand the intertwined roles of light, time, and distance in interpreting the vast signals that the universe offers to us. Every observation we make, every glimpse into the night sky is fundamentally a message sent over unimaginable expanses of space and epochs of time, carried by photons that have traveled vast distances. The relationship between these three pillars, light, time, and distance, not only shapes how we perceive the universe, but also sets inherent limitations on what and when we can know. Let us delve deeply into this fascinating interplay. First and foremost, light acts as our cosmic messenger. In the vacuum of space, light travels at approximately 299,692 kilometers per second, a constant speed that establishes a universal speed limit according to Einstein's special relativity. Photons, the particles of light, ferry information from stars, galaxies, and cosmic phenomena to our telescopes and detectors. However, the immense scales involved mean that even at this remarkable speed, light takes significant time to traverse cosmic distances. For example, the light we see from the closest star beyond the Sun, Proxima Centauri, takes about 4.24 years to reach Earth. Moving further afield, when we observe distant galaxies billions of light years away, we receive photons that began their journey billions of years ago, offering a direct window into the universe's ancient past. This intrinsic link of light to time forms the concept known as lookback time. Observing distant objects entails seeing them as they were when the photons left them, not as they are right now. Because of this, astronomy often resembles a kind of cosmic archaeology, studying the universe's history layer by layer, deciphering clues embedded in the light that arrives after tremendous journeys through space-time. When we look at very distant galaxies, or the cosmic microwave background radiation, we are effectively traveling backward in time, witnessing the universe at earlier and earlier stages of its evolution. Understanding distance on these colossal scales, however, is more nuanced than simply translating travel time of light. The universe's expansion complicates measures of distance because space itself is stretching. Distances measured today are not necessarily the distances light traveled during its journey. This leads astrophysicists to employ different types of distance definitions, tailored to the context of observation and theory. One of the most common measures is the co-moving distance, which factors in the expansion of the universe and represents a fixed coordinate system expanding with space. It allows for a consistent frame to compare the positions of distant objects over cosmic time. Another important concept is the luminosity distance, tied to how bright an object appears, which is crucial for estimating distances when direct measurements are challenging. Alongside this is the angular diameter distance, which relates to how large an object appears in the sky, often used for objects with known sizes. Each of these distances reflects a different facet of how light, time, and the universe's geometry interplay. These notions are a departure from the everyday understanding of distance and reveal how profoundly relative and dynamic cosmic measurements are. They demand that we account for the universe's metric expansion. To put it simply, while photons travel toward us, the very fabric of space stretches, often increasing the space between source and observer, even as light moves closer. This sometimes paradoxical behavior is fundamental to cosmology, and can mean that photons emitted from some galaxies are now located far beyond the extent of the observable universe, or even that those galaxies themselves are receding from us faster than light locally due to this expansion. The expansion of space also stretches the wavelength of the traveling photons, a phenomenon known as redshift. Redshift is pivotal in interpreting cosmic signals because it provides direct insight into the rate of cosmic expansion at different epochs. Light emitted with a certain wavelength becomes longer and less energetic as it traverses an expanding universe, shifting toward the red end of the spectrum. The higher the redshift, the farther and earlier the light was emitted. Thus, redshift operates as a cosmic chronometer, helping astronomers determine distances and the look-back times to observed objects. When we observe distant galaxies or quasars with high redshifts, we are seeing them as they were billions of years ago, sometimes less than a billion years after the Big Bang. This capability has transformed our understanding of cosmic evolution, uncovering the formation of the first stars, the assembly of galaxies, and the emergence of large-scale cosmic structures. Redshift not only measures distance, but unlocks the temporal dimension of cosmic history. Another critical factor in interpreting cosmic signals is how time itself behaves in relativistic contexts. Due to effects predicted by Einstein's general relativity and special relativity, observers measuring the passage of time and the arrival of photons can experience phenomena such as time dilation. For extremely fast-moving objects or in strong gravitational fields, time passes differently, and emitted light's properties change accordingly. Though these effects are subtle in many cosmological contexts, they become vital when studying phenomena like neutron stars, black holes, or jets emitting relativistic particles. Perhaps the most profound illustration of light, time, and distance intersecting are the observations of the cosmic microwave background, CMB, the relic heat radiation from the nascent universe, dating back to roughly 380,000 years after the Big Bang. The CMB photons we detect today started their journey across the cosmos over 13 billion years ago. Their surprisingly uniform but slightly anisotropic temperature provides a treasure trove of information about the early universe's conditions, the density fluctuations that seeded galaxy formation, and the fundamental parameters governing cosmic evolution. Interpreting these signals demands precise measurement tools and theoretical frameworks. Telescopes equipped with sensitive detectors scan the sky across various wavelengths to capture photons arriving from different epochs and distances. Sophisticated data analysis and cosmological models help decode this ancient light to unlock the universe's secrets. In extracting meaningful knowledge, scientists also grapple with the practical challenges of cosmic noise, photon scattering, and intervening cosmic dust, which can alter or obscure signals. Overcoming such hurdles involves multi-wavelength observations, from radio waves to gamma rays, and using complementary techniques such as gravitational lensing, which uses massive objects' gravity to magnify distant sources, allowing us to see even farther into space. All these factors, a constant speed of light, cosmic expansion, time dilation, and complex distance measures, conspire to make our cosmic view a layered and richly textured narrative. Every photon arriving at our telescopes embodies a complex journey through space-time, encoding clues about not only its origin, but also the voyage through an ever-changing universe. Recognizing this profound linkage inspires a humbling appreciation. We are not merely observers of distant stars and galaxies, but time travelers, peeking through windows opening onto ancient cosmic epochs. The way we interpret these cosmic signals is thus not just a scientific endeavor, but a deep connection, bridging time and space. As we look forward, the next logical step is to consider how the known age of the universe sets temporal boundaries on these observations, anchoring our chronicle of cosmic history. Understanding these limits further clarifies how our knowledge unfolds within the grand cosmic time frame and prepares us to explore the implications of the universe's finite lifespan. As we delve deeper into the cosmos, one of the fundamental parameters that shapes our understanding of the universe, its structure, and the limits of our observations is time itself. Specifically, the age of the universe. The age of approximately 13.8 billion years is the temporal backbone upon which much of modern cosmology rests. It provides the clock that sets crucial boundaries on what can be observed, known, and even comprehended within the cosmic expanse. To appreciate these temporal boundaries fully, let us embark on a detailed exploration of how we determine the universe's age, what this age implies for observation, and how it frames the grand cosmic narrative. The age of the universe represents the time elapsed since the Big Bang, the singular event that marked the beginning of space-time, energy, and matter as we understand them. Unlike simpler calendars measuring days or years, the cosmic age is derived from sophisticated observations and theoretical frameworks combined to chart a timeline stretching back to the dawn of all existence. One of the principal methods for determining the universe's age involves observing the cosmic microwave background radiation, or CMB, the afterglow of the hot, dense, early universe. This faint microwave radiation pervades all space, originating roughly 380,000 years after the Big Bang, when the universe cooled enough for photons to travel freely. Satellites like COBE, WMAP, and more recently, the Planck spacecraft, have measured the CMB's temperature fluctuations with extraordinary precision. These measurements feed into the standard cosmological model, allowing scientists to extract parameters such as the Hubble constant, the universe's rate of expansion, and the density of various cosmic components. By combining these observations with Einstein's general relativity and the Friedmann equations that describe cosmic expansion, researchers can effectively run the cosmic clock backward, estimating the time elapsed since the initial singularity. This calculated age, presently about 13.8 billion years with a margin of less than 1%, serves as a temporal boundary that limits the maximum look-back time available in observations. But beyond CMB measurements, other independent techniques help cross-validate the universe's age. Stellar evolution modeling is one such crucial method. Stars act as cosmic chronometers. By studying the oldest star clusters, such as globular clusters within our Milky Way, astrophysicists estimate how long it has taken for these densely packed star groups to form and evolve. These star ages provide a minimum age for the universe, since the cosmos must be at least as old as its oldest stars. These estimates have historically hovered around 12 to 13 billion years, consistent with and reinforcing the CMB-derived age. White dwarf stars, the faded remnants of sun-like stars cooling over time, offer another independent clock. By examining the distribution of white dwarfs' temperatures and luminosities, astronomers can infer cooling timescales that again complement other age measurements. The interplay of these methods builds a coherent temporal framework, situating the origin of all cosmic phenomena firmly within a timeline that extends back nearly 14 billion years. This temporal boundary directly shapes what we can see when looking into the cosmos. Essentially, the finite age of the universe restricts the maximum possible distance light could have traveled to reach us, thereby setting a limit on the observable universe's size and the cosmic horizon's location. This notion manifests as the look-back time mentioned previously. When we observe a galaxy a billion light-years away, the photons now reaching Earth started their journey a billion years ago, showing us a snapshot of that galaxy as it existed 1 billion years in the past. But since the universe is only 13.8 billion years old, it is impossible to observe anything older or more distant than the limit imposed by this age, adjusted for the universe's expansion. Moreover, the universe's finite lifespan implies a galaxy that existed beyond this temporal boundary, if it existed at all, could not have emitted light to reach us by now. This provides a causal constraint, a fundamental temporal horizon that governs what can ever be observed or known. Interestingly, the age of the universe also enriches our understanding of cosmic evolution. It provides the framework in which events such as the formation of the first atoms, stars, galaxies, and large-scale structures occurred. For instance, the formation of the first hydrogen atoms, the epoch called recombination, happened about 380,000 years after the Big Bang. First stars appeared perhaps a few 100 million years later, and galaxies gradually assembled over billions of years. Knowing the universe's age allows us to place these milestones within a grand chronological sequence, enabling a coherent narrative of cosmic history. The age also imposes limits on theoretical models and hypotheses about the universe's origin and destiny. For example, any credible theory about the Big Bang or alternative cosmologies must be compatible with the empirical age. Similarly, discussions about the universe's ultimate fate, whether a continued expansion leading to heat death, a big crunch collapse, or more exotic scenarios, rely on a clear understanding of the universe's temporal boundaries and rate of aging. It is important to realize that this age does not represent a fixed, universally agreed upon figure, but is a remarkably precise estimate based on current best measurements and models. Ongoing research and improved observations continue to refine this value. For instance, recently, researchers faced a subtle tension known as the Hubble tension, where local measurements of the expansion rate suggest slightly different values than those inferred from CMB data, potentially affecting age estimates. Resolving this discrepancy remains one of cosmology's hottest frontiers and might unveil new physics or refine our temporal understanding. Furthermore, the age of the universe sets a profound existential frame for humanity. We exist not just spatially, but temporally situated within this vast cosmic timeline. Our solar system formed approximately 4.6 billion years ago, a significant fraction, but well after the universe's birth. Life's evolution, and indeed the entire human story, occupies a small slice of this extensive cosmic epoch. Yet it owes its context to the temporal unfolding of cosmic events seeded by the universe's age. In summary, the finite age of the universe fundamentally bounds our observations, knowledge, and understanding. It restricts how far back in time our cosmic gaze can reach, and in doing so, delineates a temporal horizon as real and meaningful as any spatial boundary. This horizon connects directly to the observable universe and the cosmic horizon, creating a multidimensional limit intersecting space and time. As we advance, the natural progression is to investigate the role of the speed of light, nature's universal speed limit, and how it governs these temporal and spatial boundaries. Together, the age of the universe and the speed of light interlace to define the ultimate limits of what we can observe, know, and ponder about the cosmos. Building upon our exploration of the universe's age and how it imposes temporal boundaries, we now turn to a fundamental and pervasive rule that governs all cosmic communication and motion: the speed of light. This universal constant, approximately 299,892 kilometers per second in vacuum, is far more than just an extraordinary velocity. It serves as the ultimate speed limit for energy, matter, and information throughout the cosmos. The speed of light shapes not only our ability to observe the universe, but also the very structure of space and time, defining the maximum pace at which cause and effect propagate. Understanding this principle is central to grasping the ultimate cosmic limits. Historically, the constancy of the speed of light emerged as a revolutionary insight, culminating in Albert Einstein's theory of special relativity in 1905. Prior to this groundbreaking work, scientists believed that the speed of light might vary according to the observer's frame of reference, much like sound or other waves in a medium. However, experiments such as the Michelson-Morley experiment demonstrated that light's speed remains constant regardless of the observer's motion, a fact that demanded a fundamental re-evaluation of space and time. Einstein's theory established that the speed of light in vacuum is invariant and forms the cosmic speed limit. No object with mass can accelerate to or exceed this speed, and information cannot be transmitted faster than light without violating causality. This constancy implies profound consequences. Lengths contract, time dilates, and simultaneity becomes relative to observers' frames of reference. All these phenomena are deeply encoded into the fabric of reality, influencing everything from particle interactions to the evolution of galaxies. On a cosmic scale, the speed of light restricts how quickly signals can travel across the vast distances between stars and galaxies. When we observe distant objects, there is an inherent delay in the arrival of photons because nothing can outrun light. This delay imposes the fundamental observational constraint that the most distant signals we detect come from events that happened billions of years ago. In other words, our view of the universe is always a glimpse into its past, as information cannot arrive instantaneously. The speed of light also governs the behavior of gravitational influences and the propagation of other fundamental forces that rely on particle exchange. In Einstein's general relativity, changes in the gravitational field propagate at the speed of light, meaning that any cosmic ripples, such as gravitational waves generated by black hole mergers, have a finite velocity. The recent direct detections of gravitational waves have validated these ideas, confirming that even gravity respects this supreme speed limit. Remarkably, while the speed of light constrains the motion of objects within space, it does not limit the expansion of space itself. The universe's metric expansion allows distant galaxies to move away from us at an effective speed greater than that of light. This does not violate relativity because the galaxies are not moving through space faster than light, but rather carried apart as space itself stretches. This subtlety lies at the heart of understanding concepts such as the cosmic horizon and the limits of observability. This cosmic speed limit also forms the basis for the notion of causality, the principle that cause precedes effect. If information could travel faster than light, events could potentially be observed before their causes, upending the logical sequence of time and undermining the predictability of physics. The speed of light thus anchors the temporal order of the universe and preserves the consistency of physical laws. On the quantum realm, the speed of light still plays a critical role. Quantum entanglement, which might suggest instantaneous connections between particles regardless of distance, interestingly does not allow faster-than-light communication. The speed of light remains the ultimate ceiling for information transfer. Experiments have confirmed this, reinforcing the fundamental respect for this cosmic boundary across all scales. The practical implications of the speed of light extend even to human technologies and aspirations. For example, space probes sent to explore our solar system and potentially beyond must contend with communication delays imposed by finite signal speeds, impacting mission planning and control. Concepts such as interstellar travel confront this speed limit as a formidable hurdle. Accelerating spacecraft to significant fractions of the speed of light requires enormous energy, and exceeding it is considered impossible with our current understanding. Moreover, the speed of light sets intrinsic limits on observational astronomy. Events occurring in regions of space so distant that their light hasn't arrived, yet remain forever beyond our current knowledge. This places a hard cap on the volume of the universe accessible to observation, echoing the limits imposed by the cosmic horizon and the universe's age. In the vast symphony of the cosmos, the speed of light acts almost like the tempo, regulating the rhythm of cosmic events and the flow of information. It shapes how galaxies evolve, how signals traverse the abyss of space, and how we understand the unfolding story of the universe. By embracing this constant, we enter a realm of physics marked by wonder, precision, and deep constraints. A reality in which the seemingly boundless becomes elegantly bounded. Looking forward from this foundational principle, one can start to interpret more subtle cosmic clues. The stretching of light via redshift, the measurement of distances through the time taken by photons to traverse space, and how signals deepen our grasp of history embedded within the observable universe. These themes naturally guide us toward the next phase of our cosmic exploration: redshift and lookback time. Tools that peel back the layers of the deep past through the prism of light itself. The speed of light thus stands not just as a fundamental constant, but as a sentinel at the edge of everything we can experience, learn, and dream, an unyielding boundary woven into the very nature of the cosmos. Having established the critical role the speed of light plays in governing our cosmic observations, we now delve into two intimately connected concepts that serve as our key to peering into the deep past of the universe: redshift and lookback time. These phenomena not only allow us to measure distances across unimaginable expanses, but also reveal the unfolding story of cosmic history, showing us the universe as it was billions of years ago rather than as it is today. They offer a temporal and spatial map, a cosmic clock, and ruler intertwined, guiding us through the universe's vast epochs. Redshift, in its simplest form, refers to the process by which the wavelength of electromagnetic radiation, including visible light, is stretched toward longer, redder wavelengths. This effect was first observed early in the 20th century, and through decades of astute study, astronomers uncovered that distant galaxies exhibit spectral lines shifted toward the red end of the spectrum. This indicated that these galaxies were moving away from us, a phenomenon now understood as a signature of the universe's expansion. The redshift parameter, typically denoted as Z, quantifies the degree by which light has been stretched due to cosmic expansion. For small values of Z, redshift correlates with velocity via the Doppler effect, much like the change in pitch of a passing siren, but over cosmological distances, the expansion of space itself dominantly drives the change. In these contexts, galaxies are not just moving through space. Space is expanding between us and them, increasing the wavelengths of photons traveling toward us. Mathematically, redshift is defined by the ratio of observed wavelength to emitted wavelength -1, expressed as z bar sort L observed on ort sort torts LL emitted. 1. A higher redshift corresponds to light emitted further back in time from more distant regions, which has been stretched more by the expanding universe. Through redshift measurements, astronomers determine crucial properties: how fast an object is receding, how far away it is, and effectively, how far back in time we are looking. Lookback time refers exactly to that last idea, the finite time light takes to travel from an object to us. Observing an object at a high redshift means we are seeing it as it was billions of years ago. This concept transforms cosmology into a kind of historical science, offering snapshots of the universe at various ages, from its infancy through to its present maturity. For example, a galaxy observed at a redshift z of about 7 corresponds to light that left it roughly 13 billion years ago, less than a billion years after the Big Bang. This means the image we receive is not its current state, but a deep glimpse into its early formation stages. Such observations have revolutionized our understanding by revealing the timeline of star formation, galaxy assembly, and the processes that shaped large-scale structure. Equally important, redshift and lookback time underpin the construction of the cosmic distance ladder, a series of methods by which astronomers measure distances to celestial objects. At nearby scales, direct parallax measurements suffice. But as we reach farther into space, redshift becomes a vital indirect measure tied to the geometry and expansion rate of the universe. Of course, interpreting redshift isn't straightforward. Because the universe's expansion accelerates, thanks in part to dark energy, the relationship between redshift, distance, and lookback time is non-linear and cosmological model-dependent. Accurate cosmological parameters, including the Hubble constant, which quantifies expansion rate, dark energy density, and matter density, are essential inputs when converting redshift into meaningful time and distance scales. Observationally, astronomers utilize spectroscopy to detect characteristic emission or absorption lines produced by elements within galaxies. These spectral fingerprints shift toward the red end of the spectrum in distant galaxies, providing precise redshift measurements. Complementing this, imaging surveys capture galaxies across a range of wavelengths, revealing their morphology, star formation rates, and other properties at varied lookback times. Perhaps one of the most striking applications of redshift and lookback time lies in the study of cosmic dawn and the epoch of rionization, the era during which the first stars and galaxies ignited and began to ionize the intergalactic medium. Observing galaxies and quasars at extremely high redshifts, sometimes Z greater than 10, allows scientists to study conditions mere hundreds of millions of years after the Big Bang, providing insight into how complexity emerged from primordial simplicity. Moreover, redshift impacts how we interpret the universe's background radiation. The cosmic microwave background, CMB itself, is a highly redshifted relic of the universe's early hot plasma, cooled through expansion to microwave frequencies today. Its remarkable uniformity and slight fluctuations encode the universe's conditions at approximately 380,000 years old. An intriguing consequence of redshift and cosmic expansion is time dilation. Distant supernovae and variable objects appear to evolve more slowly to us because the expansion stretches time intervals in addition to wavelengths. This phenomenon has practical implications for measuring distances and contributes to discoveries related to cosmic acceleration. These magnificent insights, however, deepen the enigma of cosmic boundaries. There remain distances and times so distant that their signals have not reached us, constrained fundamentally by the combined effects of redshift, cosmic expansion, the universe's age, and the speed of light. These limits color the edges of the observable universe and implicitly define our cosmic horizon. Through redshift and lookback time, astronomy transcends immediate observation and becomes an investigation of cosmic history. Every photon arriving from a faraway galaxy is a time capsule, a storyteller from eons ago. Interpreting these stories demands patience, precision, and ever-advancing technology as we strive to map the universe's timeline and unravel the tapestry of its evolution. In the next chapter of our journey, we will explore the cosmic microwave background in greater detail, the farthest and oldest light we can detect, which forms a unique cosmic milestone. It stands as a border between the observable universe's infancy and the exceedingly rich structure that followed, providing unparalleled insights into the ultimate cosmic limits of observation. As we journey deeper into the understanding of cosmic limits, we arrive at a remarkable milestone in the history of the universe, the cosmic microwave background, or CMB. Often described as the afterglow of the Big Bang, the CMB represents the farthest and oldest light that we can detect, marking the ultimate observational frontier in our quest to glimpse the early universe. It is the boundary where the previously opaque primordial cosmos became transparent, allowing photons to stream freely and eventually reach us after an incredible journey across 13.8 billion years of cosmic evolution. To truly appreciate the significance of the CMB, we must first understand the conditions of the universe before its release. In the first hundreds of thousands of years after the Big Bang, the universe was a hot, dense plasma of particles, protons, electrons, photons, and neutrons, existing in a seething, energetic soup. Photons were constantly scattering off free electrons, unable to travel freely. This fog meant that the universe was essentially opaque, preventing any light from escaping and traveling unimpeded. About 380,000 years after the Big Bang, the universe had expanded and cooled sufficiently, dropping to about 3,000 Kelvin for electrons and protons to combine into neutral hydrogen atoms, a process called recombination. With electrons no longer freely roaming to scatter photons, photons could suddenly travel vast distances without interruption. This transition marked a cosmic awakening, releasing a flood of light into space, effectively forming a snapshot of the universe at that primordial moment. This ancient light, initially emitted at visible and infrared wavelengths, has journeyed through the expanding universe for nearly 14 billion years. En route, the universe's expansion has stretched the photon's wavelengths from the shorter, high-energy range into the microwave region of the electromagnetic spectrum that we detect today. The CMB now arrives at us as a faint but pervasive glow at a chilly 2.7 Kelvin above absolute zero, uniform in almost all directions to remarkable precision. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson was a watershed moment in cosmology. It provided compelling empirical evidence for the Big Bang model and helped firmly establish the standard cosmological paradigm. Since then, space missions like COBE, WMAP, and Planck have mapped the temperature fluctuations of the CMB across the sky with exquisite resolution. These tiny variations, on the order of a few parts per 100,000, encode a wealth of information about the early universe's conditions, fluctuations in density, and the seeds from which all structure formed. The CMB is not merely a static relic, but a vibrant cosmological archive. By analyzing its properties, scientists have been able to determine critical parameters, including the universe's shape, composition, ordinary matter, dark matter, and dark energy, age, and rate of expansion. The minute anisotropies correspond to quantum fluctuations amplified during the inflationary epoch, a brief moment of exponential expansion that imprinted these primordial patterns. As the farthest light we can see, the CMB forms the ultimate observational horizon in the temporal dimension. No electromagnetic signals from earlier than this epoch can reach us because before recombination, photons were trapped and constantly scattered. Thus, the CMB marks the surface of last scattering, a cosmic photosphere beyond which traditional light cannot inform us about preceding moments. The fact that this boundary exists reinforces the idea that the observable universe is constrained not just spatially, but temporally. We can look back to a faint glow emitted when the universe was only a few 100,000 years old, a tiny fraction of its current age, but not earlier using electromagnetic radiation. However, researchers have developed other innovative methods, such as studying neutrinos or gravitational waves from the very early universe, which might someday reveal information beyond the CMB's veil. But so far, the CMB remains our primary window into the universe's first light. The surface of last scattering is a sphere around us, about 46 billion light-years in radius, meaning that we receive CMB photons even from regions of space presently far beyond the reach of stars and galaxies. This reflects the difference between the time light was emitted and the current location of the source. The expansion of space has greatly increased distances since emission. Observationally, the CMB appears near perfectly isotropic, yet the tiny temperature fluctuations are crucial. They correspond to slight variations in density that under gravity's pull evolved into the cosmic web of galaxies and clusters. Mapping these fluctuations reveals the fundamental processes that governed early physics and guides theoretical physics in domains such as inflation, dark matter properties, and the nature of dark energy. Moreover, the CMB's polarization patterns provide complementary information, allowing cosmologists to probe phenomena such as primordial gravitational waves and the interaction of photons with charged matter in the early universe. Thus, while the cosmic microwave background represents a boundary to electromagnetic observation, it is not a limitation, but rather a gateway, a source of unparalleled insight into the universe's infancy and evolution. It frames the limits of our cosmic vision while simultaneously illuminating the grand narrative stretching back to the almost inexplicable origins. In the context of cosmic limits, the CMB serves as a reminder that while our observable universe is vast, it is bounded by both the physics of light and the history encoded in time itself. Beyond this horizon lies the mystery of inflationary epochs, and perhaps domains forever hidden from view. As we conclude this exploration, we prepare to journey beyond the CMB, examining the role of dark energy in the universe's accelerated expansion and how it dynamically reshapes the observable boundaries, further challenging and expanding our cosmic horizons. As we advance our exploration into the ultimate cosmic limits, we encounter one of the most profound discoveries in modern cosmology: dark energy and the accelerated expansion of the universe. This mysterious force, making up about 68% of the total energy content of the cosmos, has reshaped our understanding of the universe's fate and significantly altered the boundaries of our observable cosmic horizon. Unlike the early expectations that cosmic expansion might decelerate under gravity's pull, observations reveal an accelerating expansion, causing parts of the cosmos to recede from us ever more rapidly, far beyond the reach of even the fastest signals. This phenomenon reshapes what can be observed, understood, and ultimately what lies forever beyond our grasp. The saga of discovering cosmic acceleration began in the late 1990s, when independent teams studying distant-type Ia supernovae, stellar explosions with well-understood brightness, found these standard candles were dimmer than expected. This dimness implied the universe's expansion rate was not slowing, as was widely assumed, but speeding up. This startling revelation led to the introduction of an unknown, repulsive component dubbed dark energy. While its true nature remains elusive, dark energy effectively acts as a uniform energy density pervading space, exerting a negative pressure that drives accelerated expansion. To visualize this expansion, imagine points painted on a stretching rubber sheet. Early on, the sheet's stretching slows slightly as all points pull on each other through gravity. But with dark energy dominating, the stretching accelerates, pushing points apart faster and faster. This acceleration isn't subtle. It causes distant galaxies to move away at an increasing fraction of the speed of light, eventually receding so quickly that their light will never reach us. This leads to the critical concept of the cosmic event horizon in an accelerating universe. Unlike the particle horizon, which marks the furthest distance light has traveled to reach us so far, the event horizon defines the limit beyond which events occurring now will never be observed in the future because space is expanding too rapidly. This horizon places an absolute boundary around our causal universe, a point of no return in cosmic communication, beyond which regions become permanently disconnected. As space expands at an accelerating pace, more and more galaxies cross this event horizon, fading from view and becoming unreachable. While today's observable universe includes billions of galaxies, the distant future will see this number dwindle, leaving only the local group of galaxies gravitationally bound and visible. This gradual shrinkage of the observable realm reshapes our cosmic perspective, emphasizing the transient nature of cosmic access. Dark energy's influence also modifies the large-scale geometry and destiny of the universe. The presence of a cosmological constant, or dark energy component, leads to an ever-expanding cosmos approaching a state of indefinite inflation. Galaxies moving apart, temperatures plummeting, and star formation waning, eventually ushering in a cold, dilute, dark epoch often called the heat death. While this fate lies trillions of years ahead, it represents the ultimate cosmic limit on future observations and interactions. From a theoretical standpoint, dark energy challenges our deepest physical frameworks. Einstein initially introduced the cosmological constant to maintain a static universe, but later discarded it as unnecessary when cosmic expansion was discovered. The modern revival of a similar concept to explain accelerated expansion has provoked intense theoretical efforts to understand its origin, whether as a constant vacuum energy, a dynamic field like quintessence, or as a signature of even more exotic physics. These mysteries intertwine with fundamental physics, quantum theory, and gravity, opening questions about whether dark energy represents an inherent property of space or a gateway to new laws of nature. Measuring how the acceleration rate evolves may help distinguish between theories and refine our picture of cosmic boundaries. Observational surveys employing supernovae, baryon acoustic oscillations, cosmic microwave background measurements, and weak gravitational lensing continue to map dark energy's influence, seeking to quantify its properties and influence on cosmic expansion. Planned missions and telescopes promise unprecedented precision, potentially unlocking secrets of the universe's accelerating growth. In the context of cosmic limits, dark energy fundamentally changes our relationship to the universe's size and age. It extends the horizon of now in time, but contracts the future region that remains causally connected. The expansion boundaries set by dark energy are dynamic and ever-shifting, constantly redrawing the map of the visible and the unknowable. This accelerating expansion also deepens philosophical reflections. The parts of the universe we can meaningfully communicate or receive signals from will shrink over cosmic time. Our window into the cosmos is both enormous by human standards, yet impermanent on cosmic scales. As we recognize dark energy as a dominant player shaping cosmic limits, the stage is set for exploring one of the universe's most enigmatic structures, event horizons associated with black holes and cosmological boundaries, the ultimate points of no return. These horizons represent not only spatial boundaries, but profound limits on information, observation, and understanding, marking the edge between the known and the unknowable. Thus, the revelation of dark energy transforms the cosmic limits we perceive, expanding some boundaries and contracting others, inviting us to rethink the nature of the universe and our place within it. Having traversed the vast landscape of cosmic observation, horizons, and the accelerating universe, we now confront a realm where the ultimate limits of observation and knowledge are not only defined by cosmic expanses, but by gravity's most extreme manifestations, event horizons surrounding black holes and similarly profound boundaries that represent points of no return. Event horizons are more than abstract theoretical constructs. They are tangible edges marking where the known laws of physics confront their most intense tests, and beyond which information and light cannot escape. Our journey into these enigmatic frontiers reveals profound insights into space, time, causality, and the fundamental nature of reality. To understand event horizons, we begin with black holes, astrophysical objects formed from the gravitational collapse of massive stars or through mergers and accretion. A black hole's mass is compressed into such an incredible density that its gravitational pull prevents anything, including light, from escaping once it crosses a specific boundary. The event horizon. This boundary is not a physical surface, but a mathematical surface in space-time. It effectively separates the black hole's interior, a region causally disconnected from the outside universe, from the external realm. Crossing the event horizon inexorably leads toward the singularity, where classical physics, as we know it, breaks down. The defining feature of an event horizon is its causal nature. Information, matter, or radiation that crosses it outward cannot return. Conversely, no signals can enter from inside it to influence the outside observer. This property makes event horizons the ultimate cosmic barrier and represents a stark limit on observation and knowledge. From our vantage point in the universe, the interiors of black holes remain forever hidden. A cosmic secret protected by the laws of general relativity and augmented by the universe's strict causal ordering. Mathematically, the event horizon's location depends on the black hole's mass, charge, and angular momentum. For the simplest, non-rotating black hole described by the Schwarzschild solution, the event horizon is a spherical surface at a radius known as the Schwarzschild radius. For more complex rotating black holes described by the Kerr solution, the geometry of the event horizon becomes more intricate, yet the fundamental property of being a one-way causal boundary remains. What makes event horizons deeply fascinating is their intimate connection to thermodynamics and quantum theory. In the 1970s, physicist Stephen Hawking demonstrated that black holes emit radiation, aptly called Hawking radiation, due to quantum effects near the event horizon. This radiation means that black holes are not entirely black, but slowly evaporate over extremely long timescales, posing intriguing questions about the fate of information that crosses the horizon and challenging our understanding of quantum mechanics and gravity's reconciliation. Event horizons are not exclusive to black holes. In cosmology, the accelerated expansion of the universe driven by dark energy also induces a cosmic event horizon. This horizon separates regions of space from which signals emitted now will never reach us in the future, due to the increasingly rapid expansion of the intervening space. This cosmological horizon imposes an ultimate causal limit on observation and communication, much like the black hole event horizon, but operator over vastly larger scales and driven by different physical mechanisms. Thinking more abstractly, event horizons epitomize boundaries where spacetime's causal structure alters drastically, creating enclaves inaccessible to external observers. They serve as natural laboratories for investigating the interplay of gravity, quantum mechanics, and information theory, posing fundamental puzzles encapsulated in problems like the black hole information paradox. From an observational standpoint, while the interior of a black hole lies forever out of reach, astronomers have detected and imaged phenomena closely linked to event horizons. The historic Event Horizon Telescope project synthesized data from a global array of radio telescopes to produce the first direct image of a black hole's shadow, the silhouette caused by the event horizon blocking background emission. This remarkable accomplishment provides empirical access to one of nature's most extreme cosmic boundaries. The notion of a point of no return challenges human intuition, yet it reveals the universe's profound causal structure. Event horizons act not only as spatial boundaries, but as dynamic markers dictating what can be known, seen, or measured from any vantage point. They encapsulate hard physical limits, beyond which space, time, and the flow of information take on forms that defy classical comprehension. Furthermore, when we extend the concept of horizons beyond classical black holes to the fronts of cosmological and quantum gravity contexts, event horizons stimulate ongoing theoretical work exploring how physics behaves at the limits of observation and knowledge. Ideas such as holographic principles, black hole complementarity, and quantum entanglement at horizons all stem from dragging the implications of event horizons to their deepest reaches. As we reflect on event horizons, we grasp that cosmic limits are not merely distances or times, but are fundamentally tied to conditions where causal connectivity breaks down, signaling borders of physics itself. These horizons delineate the ultimate frontiers of the universe as observed and understood. Our cosmic voyage now naturally leads us into the questions of information, how it is encoded, lost, or preserved through these horizons. This contemplation brings us to the fascinating interplay of information theory and entropy, exploring the finite limits of cosmic knowledge in terms of bits and the fundamental structure of space-time. By doing so, we continue unraveling the deepest mysteries of the cosmos, pushing against the ultimate edges of observation and understanding. As our journey through the cosmic limits continues, we arrive at a profound intersection of physics and philosophy, information and entropy, the twin pillars that define the ultimate boundaries of what the universe allows us to know. While distances, horizons, and the incessant expansion of space set tangible limits on our observations, the concepts of information and entropy penetrate deeper, framing the very nature of knowledge, uncertainty, and the fabric of reality itself. Exploring these ideas reveals how physics imposes fundamental constraints on cosmic knowledge, reminding us that the limits of understanding are woven into the universe's essence. Information, in the broadest scientific sense, refers to the arrangement and state of physical systems, a record of distinctions, structures, or configurations that can be known, measured, and transmitted. Claude Shannon's foundational work formalized information theory, quantifying information as bits and linking it intrinsically with probabilities and entropy, a measure of uncertainty or disorder. Entropy, as originally formulated in thermodynamics, quantifies the number of microscopic configurations compatible with a macroscopic state, indicating how much disorder or randomness exists. In cosmology and quantum physics, entropy takes on even more expansive roles, connecting thermodynamics, gravity, and quantum information theory. It governs how systems evolve, how processes become irreversible, and how data about the universe's state become inherently limited. When discussing the limits of cosmic knowledge, one must consider the interplay of information, entropy, and horizons. For horizons act as boundaries not just in space and time, but in the transmission and reception of information. The event horizons of black holes, for example, are prime illustrations. According to one of the most intriguing discoveries in theoretical physics, the entropy of a black hole is proportional not to its volume, but to the area of its event horizon, a principle known as the Bekenstein-Hawking entropy. This insight upended previous assumptions, hinting at a deep connection between geometry and information. Black holes thus represent extreme informational limits in the universe. Information falling into a black hole seems to disappear behind the event horizon. While classical physics implied a loss of information, contradicting quantum mechanical laws that prohibit information destruction, modern theoretical advances, particularly those invoking quantum gravity and holography, suggest that information is conserved, albeit in highly non-trivial ways encoded on the surface area of horizons. This idea matured into the holographic principle, stating that all the information contained in a volume of space can be described by data encoded on its boundary. Such a realization profoundly shifts our understanding of space, dimensionality, and the architecture of reality. It implies that the universe's maximum informational content is finite and tied fundamentally to areas rather than volumes, placing concrete constraints on the complexity and knowledge it can harbor. Beyond black holes, these informational and entropic concepts extend to the whole cosmos. The presence of horizons, cosmic event horizons due to accelerated expansion, implies that observable regions have a finite entropy and information capacity. This restricts how much can be known or even affected causally within our cosmic patch, placing bound limits on the total information the observable universe can encode. Moreover, entropy guides the arrow of time, the asymmetry that underpins our experience of past, present, and future. The second law of thermodynamics posits that entropy tends to increase, driving irreversible processes and shaping the large-scale evolution of cosmic structures. This growth of entropy is intimately linked with the expansion of the universe, the cooling of radiation, formation of galaxies, and emergence of complexity. Yet it also implies inevitable limitations. As the universe approaches heat death or maximum entropy, useful information and the capacity to distinguish ordered states will diminish. The recognition that cosmic information is fundamentally bounded by entropy injects humility into our quest for knowledge. Even with infinite computational power, the universe's physical laws restrict how much one can learn about its state or predict the future precisely. Quantum uncertainty further accentuates these limits on measurement and knowledge at the smallest scales. This relationship between information, entropy, and observation also raises intriguing philosophical questions. Is reality itself finite in its informational content? Could the universe be compared metaphorically to a huge data structure with encoded limits? How do these bounds influence consciousness, life, and even the possibility of simulating universes? Each of these themes intersects with interpretations of physical law and the scope of scientific inquiry. Practically, these limits influence fields ranging from quantum computing and black hole physics to cosmology and the search for a unified theory of quantum gravity. They drive research into understanding black hole evaporation, the nature of space-time foam at Planck scales, and the entanglement structure of quantum fields, all in pursuit of a coherent narrative that reconciles gravity with quantum mechanics. As we contemplate the universe's vastness and our place within it, the concepts of information and entropy bring us face to face with a fundamental truth. The universe has finite capacity for knowledge and observation, no matter how boundless it may appear. Horizons, expanding or fixed, not only limit light and signals, but also the information accessible to any observer. This realization sets the stage for our exploration of cosmological inflation, the epoch preceding the observable universe, imbued with its own entropic and informational dynamics. As we proceed, we will also confront even grander philosophical questions raised by hypotheses such as the multiverse and the fundamental laws bending at the Planck scale, each expanding our understanding of cosmic boundaries and limitations. In embracing the interplay of information and entropy, we recognize that cosmic limits are not mere numerical boundaries, but profound characteristics of the universe's deepest structure, intertwining physics, philosophy, and the eternal human yearning to understand the cosmos. As we continue our cosmic investigation beyond the observable universe and its intrinsic horizons, we arrive at a tantalizing epoch preceding it all: cosmological inflation. This remarkable phase, a fleeting moment of exponential expansion in the earliest instance of the universe, set the stage for everything that followed. Inflation is the primordial prelude, a profound chapter that precedes the visible universe and holds clues about the deepest boundaries of cosmic origins, structure, and limits of observation. Inflationary theory emerged in the early 1980s as a compelling solution to several puzzling observations about the universe's uniformity, geometry, and large-scale structure. Prior to its formulation, cosmologists grappled with questions such as the horizon problem. Why regions of the cosmos separated by vast distances display astonishingly uniform temperatures and densities despite never having been in causal contact? The flatness problem posed another mystery, questioning why the universe's large-scale geometry appears so precisely balanced between open and closed states, implying fine-tuned initial conditions. Inflation elegantly resolves these by positing an ultra-rapid expansion phase shortly after the Big Bang, typically between 1036 to 1032 seconds after the origin, during which space itself expanded faster than the speed of light. Though faster-than-light expansion might sound paradoxical, it does not violate relativity since it involves the stretching of space-time itself, not the movement of objects through space. This exponential growth amplified an incredibly small, causally connected volume of space to encompass regions far larger than today's observable universe, smoothing out irregularities and pushing curvature towards flatness. Inflation also provides a mechanism for generating the primordial quantum fluctuations, tiny ripples in density that later evolved under gravity into the cosmic structures we see today: galaxies, clusters, and the vast cosmic web. Observational evidence supporting inflation comes primarily from the exquisitely precise measurements of the cosmic microwave background, CMB radiation. The tiny temperature anisotropies in the CMB correspond closely with theoretical predictions of quantum fluctuations inflated to macroscopic scales. Furthermore, detailed study of the CMB's polarization offers potential windows into primordial gravitational waves, subtle imprints of inflation's violent expansion. Despite these successes, inflation also introduces uncertainties about cosmic limits and the nature of reality. The zone inflated so dramatically before what we call the Big Bang extends beyond our empirical boundaries, regions forever outside the observable universe. This pushes the cosmic horizon outward, but paradoxically cloaks significant portions of the cosmos in permanent invisibility. If inflation lasted long enough, the observable universe is potentially an infinitesimal fraction of the entire cosmos, hiding an enormous, vastly larger multiverse realm beyond. Such a multiverse, if it exists, may comprise continuously inflating bubbles, each spawning different universes with varying physical parameters, fundamental constants, or even laws of physics. Our observable cosmos could thus be just one tiny patch within a sprawling cosmic landscape. This notion challenges traditional notions of limits. The frontier of observation remains finite, but what lies outside may be boundless and forever inaccessible. Another intriguing implication of inflation is tied to the initial singularity itself. Inflation effectively smooths out conditions, making the universe's initial state less dependent on fine-tuned requirements. Still, it does not eliminate the question of the ultimate beginning, pushing it to a more primordial level, possibly involving quantum gravitational phenomena beyond current theories. Contemporary research strives to explore inflation's precise mechanisms, characterize the inflaton field or fields responsible, and connect inflationary theory with the fundamental laws governing particle physics and gravity. The quest includes probing for primordial gravitational waves through advanced cosmic surveys and examining alternatives or extensions of inflation that might reconcile theoretical challenges. In the grand narrative of cosmic limits, cosmological inflation thus represents a boundary beyond the observable, a veil behind which the earliest moments and possibly the largest structures of reality reside. It frames not only how our observable universe came into being, but also how far the fundamental boundaries of knowledge might stretch. As we prepare to move further in our exploration, the inflationary epoch primes us to contemplate ideas that extend even beyond our universe. The speculative and fascinating realm of the multiverse hypothesis, and the degrees to which such boundaries are scientific or philosophical in nature. Inflation opens the door to these profound questions, bridging the known with the vast unknown. As our examination of cosmic limits continues, we venture now beyond the familiar confines of our observable universe into the realm of the multiverse hypothesis, a speculative yet captivating idea that challenges the very notion of boundaries and the scope of reality itself. While standard cosmology describes a vast but singular universe bounded by cosmic horizons and governed by known physical laws, the multiverse concept proposes that our universe might be but one among an enormous ensemble, or even an infinite collection of universes, each with potentially different physical constants, laws, and structures. This hypothesis pushes the cosmic boundaries far beyond what we can detect, measure, or empirically verify, inviting profound questions about the nature of existence, observation, and fundamental limits. The origins of multiverse ideas stem from several lines of thought arising in modern physics and cosmology. One impetus comes directly from the inflationary paradigm discussed earlier. In some versions of cosmic inflation, particularly eternal inflation, the inflationary process never completely ends everywhere. Instead, inflation continues in some regions, spawning. As we delve deeper into the nature of the cosmos and its ultimate boundaries, a fundamental question emerges. Are there intrinsic limits embedded within the very laws of physics themselves? Beyond the observable horizons, beyond the speed of light, and even beyond the vastness suggested by multiverse theories, the laws of physics stand as gatekeepers determining what is possible, what can be measured, and what remains forever beyond our reach. Understanding whether these laws impose fundamental constraints, and if so, what those constraints entail, strikes at the core of both modern science and philosophy. The laws of physics, as currently understood, are expressed through a collection of elegant and highly successful theories. General relativity governs the force of gravity and the fabric of space-time. Quantum mechanics describes the behavior of particles and fields at the smallest scales. The standard model of particle physics integrates electromagnetic, weak, and strong interactions, and thermodynamics and statistical mechanics bridge microscopic and macroscopic realms. These frameworks have undergone rigorous experimental testing, yielding astonishingly precise predictions. Yet each also hints at inherent boundaries and unfinished understanding. One of the clearest examples of fundamental limits is found in Einstein's theory of special relativity, which establishes the speed of light in a vacuum as the ultimate speed limit. No information or matter can surpass this speed, placing an absolute constraint on causality and communication across the universe. Violating this bound, even hypothetically, leads to paradoxes such as backward time travel and causality violations, which undermine the logical consistency of physical laws. Thus, the speed of light functions as a rigid cosmic speed limit, an inviolable boundary in both theory and experiment. Similarly, quantum mechanics introduces profound limitations on measurement and knowledge through the Heisenberg uncertainty principle. At the most fundamental level, certain pairs of physical properties, such as position and momentum or energy and time, cannot be simultaneously known to arbitrary precision. This intrinsic uncertainty is not due to technological inadequacy, but is baked into the fabric of reality. It implies an irreducible fuzziness that caps the precision achievable when probing the universe, framing the limits of what can be observed and known. The interplay of quantum theory and gravitation introduces further mysteries that suggest even deeper fundamental boundaries. General relativity predicts singularities, points where density, curvature, and energy become infinite, such as the Big Bang and black hole centers. However, these singularities also signal the breakdown of classical physics. Here, quantum gravitational effects are presumed to regulate such infinities, but a complete theory of quantum gravity remains elusive. This incomplete understanding indicates fundamental limits in current physics and the possibility that new principles may emerge governing the smallest and most energetic scales. The Planck scale, characterized by lengths around 1.6 x 10 to the 35 meters, and times near 5.4 x 10 to 44 seconds, may mark the boundary at which conventional descriptions of spacetime cease to be valid. At this scale, the smooth geometry of spacetime potentially gives way to a quantum foam or discrete structure. This scale sets a fundamental limit on the resolvable distances and times, implying that any measurement beyond the Planck limit is intrinsically undefined. Such minimal scales define an absolute frontier to direct physical inquiry. Thermodynamics and the concept of entropy also introduce universal bounds. The second law of thermodynamics imposes a directionality on processes and an inexorable increase in entropy in closed systems, placing limits on energy availability and the flow of time as experienced macroscopically. In cosmological contexts, entropy sets ceilings on the information content and state ordering possible within horizons and the universe itself, entwining physical laws with informational limits. Current theoretical frontiers consider principles such as the holographic bound, which emerged from the study of black hole physics and suggests that the maximum entropy, or information content, of a region scales with its surface area rather than volume. This principle hints at a radical restructuring of how physical degrees of freedom are organized, affecting the limits on data density and computational capacity inherent in nature. Beyond these concrete constraints, ongoing debates question the universality and absoluteness of known physical laws. Certain speculative theories posit variations in constants over cosmological time or between different regions of a multiverse. Others consider that spacetime itself might emerge from more fundamental quantum entanglement structures, or that unknown physics could modify or supersede current laws at extreme energies or scales. The propensity for physics to reveal fundamental limits fuels scientific progress and philosophical inquiry alike. It frames the quest for a unified theory, often termed a theory of everything, that seamlessly merges quantum mechanics and general relativity and elucidates whether ultimate boundaries exist or if hidden layers still await discovery. In practical terms, these limits shape the design and ambition of experiments, from particle accelerators probing higher energies to telescopes pushing deeper into cosmic time and space. They influence considerations in emerging fields, such as quantum computing and information theory, and in understanding the ultimate fate of the universe. In sum, the laws of physics appear to impose fundamental limits on speed, knowledge, measurement precision, information content, and causality. Whether these limits are absolute or only approximate representations of a deeper, more intricate physical structure remains an open question. This uncertainty propels ongoing research at the frontiers of physics, drawing us ever closer to understanding the ultimate rules that govern the cosmos and the boundaries of what can be known. As we transition from considering these fundamental physical limits, we move naturally to discuss the Planck scale itself, the realm of shortest distances and smallest times, where these boundaries manifest most sharply and where the quest for new physics takes center stage. Venturing into the most profound depths of the natural world, we encounter the Planck scale, the realm where the very fabric of space and time reveals its ultimate granularity, and our current understanding of physics reaches its limits. The Planck scale stands as the frontier of the shortest distances and the smallest intervals of time conceivable according to known laws, marking the boundary at which classical notions of continuous space and smooth time cease to apply. To grasp the essence of the cosmic limits embodied by the Planck scale is to approach the foundation upon which the entire universe is constructed, and to confront the mysteries of quantum gravity and the nature of reality itself. The Planck scale derives from fundamental constants, combining Newton's gravitational constant, g, the speed of light, c, and Planck's constant, h, into natural units that define meaningful measures of length, time, mass, and energy. Specifically, the Planck length is approximately 1.616 x 10 to the 35 meters, a scale unfathomably small, roughly 20 orders of magnitude smaller than the size of a proton. Similarly, the Planck time, the time light requires to traverse one Planck length, is around 539 to 10 to 44 seconds. At these minuscule scales, the structure of spacetime is expected to be highly non-classical. Quantum fluctuations become dominant, causing spacetime itself to, as we delve deeper into the origins of the cosmos, we confront the enigmatic concept of the Big Bang singularity, a profound and puzzling point often described as the absolute beginning of our universe. This singularity, predicted by classical general relativity, is posited as the state where density, temperature, and space-time curvature become infinite, marking the theoretical boundary beyond which known physics breaks down. Grappling with this concept pushes us to the ultimate cosmic limit, the very inception of everything, where standard notions of space and time may cease to be meaningful. According to classical cosmology, extrapolating the universe's expansion backward in time leads inevitably to a moment when the scale factor, the measure of the universe's size, shrinks to zero. At this instant, commonly referred to as the singularity at time zero, the universe is infinitely dense, and conventional physics ceases to provide a coherent description. This idea arises naturally from solutions to Einstein's field equations under the assumption that the universe is homogeneous and isotropic, an approach modeled by the Friedmann-Lemaitre-Robertson-Walker (FLRW) metric. However, the infinite quantities implied by a singularity suggest physical and mathematical inadequacies in the classical theory. Infinity in physics often signals the breakdown of models rather than real physical states. It raises critical questions. Is the singularity truly a point of origin, or simply a placeholder for an as-yet unknown description of the universe's earliest moments? Can the notion of a cosmic beginning be meaningfully defined if spacetime itself emerges from more fundamental pre-geometric structures? Quantum mechanics, the theory governing the behavior of particles and fields at the smallest scales, plays a pivotal role here. Its integration with gravity, quantum gravity, is widely believed necessary to resolve the singularity problem, providing a finite and well-defined framework for the universe's genesis. Several approaches, including string theory and loop quantum gravity, attempt to replace the singularity with a quantum bounce or another non-singular mechanism, where the classical singularity is smoothed out by quantum effects. The idea of the Big Bang as an absolute beginning also confronts philosophical and metaphysical implications. If time itself originates at the singularity, then questions about what preceded the Big Bang may become ill-defined or meaningless within traditional temporal frameworks. This forces reconsideration of causality and the meaning of beginning in a temporal sense. Some models propose a pre-Big Bang epoch, or scenarios such as cyclical universes, where a preceding contraction phase leads to expansion, evading the concept of a singular starting point. Observationally, while the Big Bang singularity remains beyond direct empirical reach, the cosmic microwave background radiation and large-scale structure data serve as windows into the earliest observable epochs, bridging the gap between theoretical extrapolations and physical evidence. Attempts to detect signatures of quantum gravitational phenomena, such as primordial gravitational waves, aspire to shed light on conditions near the Planck era, just after the hypothesized singularity. Thus, the Big Bang singularity remains at once a critical boundary in cosmology and a beacon guiding theoretical advances. It emphasizes the limits of classical understanding and opens the door to new physics, compelling physicists to expand and refine our theories of space, time, and matter. As we progress, these profound themes naturally connect to ideas about cosmic censorship, principles that may hide singularities behind horizons, ensuring the universe's predictability and safeguarding observers from their disruptive effects. Exploring these connections further enriches our understanding of what can be observed, known, and ultimately transcended in the grand saga of the cosmos. In our continued exploration of the universe's profound mysteries, we now consider the principle known as cosmic censorship, a provocative theoretical idea addressing the very nature of what parts of the cosmos remain forever hidden from observation, and what, due to physical laws, can never be known. This concept grapples with the question: are there regions or singularities in the universe cloaked from all possible view, shielding their secrets behind impenetrable barriers? More broadly, cosmic censorship seeks to explain the limits of our observational access imposed by the fundamental structure of space-time itself. The genesis of cosmic censorship lies in the study of black holes and gravitational singularities within Einstein's general theory of relativity. Singularities are regions where densities and curvatures become infinite, and classical physical descriptions cease to apply. The best-known examples are the singularities predicted to reside at the heart of black holes and, theoretically, at the universe's beginning, the Big Bang singularity. One of the pressing questions is whether such singularities could, under some conditions, be naked, exposed to the wider universe without protective horizons to hide behind. In the confident yet cautious tone of theoretical physics, cosmic censorship was proposed in the 1960s and 1970s by Roger Penrose and others to preserve the universe's predictability. It posits that singularities, while possibly inevitable, are always enclosed within event horizons, horizons that prevent direct observational access and preserve causal consistency. This is known as the weak cosmic censorship hypothesis. The principle safeguards the universe from pathological behavior and breakdowns in causality that naked singularities could cause, maintaining that the laws of physics remain fair and communicable to observers outside these horizons. There is also a strong cosmic censorship hypothesis, suggesting that the deterministic nature of general relativity remains intact in all physical situations, forbidding the possibility of extending spacetime beyond singularities in unpredictable ways. Together, these ideas uphold the notion that the universe hides its most extreme and enigmatic regions behind cloaks from which no light or information can escape. However, despite the compelling theoretical framework, cosmic censorship remains a hypothesis and is yet unproven. Mathematical investigations and numerical simulations of Einstein's equations expose scenarios, often highly idealized or involving exotic matter, that challenge cosmic censorship by producing naked singularities. These remain subjects of intense research, as their existence would profoundly alter our understanding of cosmic limits and potentially allow for exotic physics, such as violations of causality or novel observable phenomena. Aside from pure gravity, the principle also frames what can be observed about the origin or interior of black holes. For instance, the event horizon marks an ultimate veil, beyond which lies a realm inaccessible even in principle, posing limits on empirical knowledge and observational astronomy. While indirect effects provide hints about processes within these hidden regions, the exact state inside remains fundamentally unknowable, wrapped in a cosmic shroud. In cosmology, cosmic censorship hints at why the Big Bang singularity, or any other primordial singularities, are safely censored behind the cosmological horizon. We can glimpse up to a point through the relic photons of the cosmic microwave background. But what lies beneath that boundary, the initial singularity, or whatever physics supersedes it, is hidden from direct view. Thus, cosmic censorship establishes profound boundaries not only on spatial observability, but on the principled limits of knowledge itself. It assures us that while the universe may contain unfathomable regions, the laws governing our accessible reality remain consistent and causal. It also encourages philosophical reflections on the nature of knowledge, observation, and the universe's opacity. What does it mean for something to be fundamentally unseeable or unknowable? How do these cosmic secrets shape our understanding of reality? Can future theories surmount these barriers, or are some boundaries insurmountable by principle? In wrapping our thoughts on cosmic censorship, we recognize it as a guardian of cosmic order, a principle that delineates an ultimate veil in the universe, a profound limit on observation and knowledge. It bridges physics and philosophy, highlighting the interplay between what exists and what can be perceived. Our gaze now turns forward to future horizons, the dynamic boundaries that will mark the end of the visible universe as cosmic expansion and dark energy continue their relentless influence, forever altering the horizon of what is observable. As we continue our exploration of cosmic boundaries, our gaze now turns towards the future horizons, the dynamic and evolving edges that will define the end of the visible universe as we move forward through time. Unlike the cosmic horizon fixed by the speed of light and the universe's age, future horizons are shaped by the relentless expansion of space itself, driven increasingly by mysterious dark energy. These horizons imply that parts of the cosmos currently within our reach may eventually slip beyond the limits of what we can ever observe or influence, fundamentally altering the cosmic landscape and posing the ultimate challenge to our understanding of the universe. Current cosmological observations indicate that the expansion of the universe is accelerating due to dark energy's repulsive influence. As a result, galaxies not tightly gravitationally bound to our own local group are receding at an ever-increasing pace. Eventually, these vast cosmic neighbors will move away so quickly that their light will no longer be able to catch up with us. In practical terms, their images will fade, their signals cease, and they will vanish from our observable universe. This phenomenon defines the cosmological event horizon, a boundary in spacetime beyond which events occurring now or in the future can never affect an observer. Signals emitted beyond this horizon will never reach Earth, no matter how long we wait. Unlike the particle horizon, which is a boundary determined by how far light has traveled since the Big Bang, the event horizon sets an absolute limit on the causal structure of the universe in the future. Thus, it dictates what portions of the cosmos will remain forever invisible to us as time marches on. The effect of this expanding future horizon is profound. In the very distant future, perhaps tens or hundreds of billions of years from now, only gravitationally bound systems, such as our Milky Way galaxy and its close neighbors, will remain visible. Distant galaxies, clusters, and cosmic structures will recede beyond the event horizon and vanish from the sky. The universe, as seen from Earth, will appear increasingly desolate and dark, resembling a lonely island in an accelerating sea of expanding space. This isolation has deep consequences for our quest to understand the cosmos. Many clues we rely on today: distant supernovae that revealed cosmic acceleration, the cosmic microwave background radiation providing a picture of the early universe, and large-scale structures tracing cosmic evolution, will become inaccessible. Future civilizations, if any exist, will find it extraordinarily difficult to reconstruct the full cosmological history with such a limited vantage point. Furthermore, the future horizon is not a static line, but evolves over time. As the expansion accelerates, more and more regions cross the event horizon, and the volume of the observable universe shrinks in co-moving coordinates. This dynamic boundary shapes how cosmic information and causal interactions unfold, emphasizing temporal limits to knowledge as well as spatial ones. An intriguing philosophical dimension arises from this. The transient nature of cosmic observability implies that our current epoch is privileged cosmologically, a rare window when the universe is rich with observable structures and signals. Past eras were opaque or uniform, and future eras will be isolated and lonely. This cosmic coincidence invites reflection on how observers and their knowledge may be situated within the universe's grand timeline. In addition to cosmological event horizons, theoretical frameworks suggest other future horizons related to speculative physics and altered cosmic fate scenarios. For example, if dark energy evolves or decays, leading to changes in expansion rates, the boundaries of visibility could shift differently. In more extreme cases, such as the hypothetical Big Rip scenario, accelerated expansion could eventually tear apart all matter, even down to atomic scales, introducing cataclysmic horizons marking the ultimate end of structures. Understanding the future horizons thus intertwines cosmology, astrophysics, fundamental physics, and even existential contemplation. It challenges us to consider the permanence or impermanence of what is presently observable and drives the scientific pursuit to grasp the forces that govern the universe's destiny. In sum, future horizons crystallize the idea that the universe's observable limits are not merely spatial or historical, but profoundly temporal. As the cosmos ages, observable boundaries shift, contracting the volume from which we can receive information and altering our cosmic perspective. These horizons define the ultimate frontiers of observation and influence, marking the threshold where the visible universe ends and the permanently unseen begins. Our understanding of future horizons naturally leads into considerations of life's cosmic limits, how habitable environments arise and persist within this changing observable cosmos. The interplay of cosmic evolution and life's fragile niches adds a human dimension to these ultimate cosmic boundaries, uniting the vast and the intimate in the grand narrative of existence. Stepping beyond the vast inanimate structures and boundaries of the cosmos, we now turn to a profoundly compelling facet of the universe's grand narrative: the cosmic limits that govern life itself. Life's cosmic limits, intertwined deeply with the conditions that permit habitability, paint a nuanced picture of where, when, and how life might arise and persist in the vast arena of space and time. Understanding this habitable universe not only frames the extent of biological possibilities in the cosmos, but also stretches our comprehension of ultimate physical and temporal boundaries. The concept of habitability traditionally centers on environments capable of sustaining liquid water, a solvent intimately tied to life as we know it on Earth. However, habitability is a multi-scaled phenomenon requiring a delicate balance of astrophysical, planetary, chemical, and even biological factors. From the scale of galaxies to individual stars and planets, various cosmic limits govern where the conditions favorable for life emerge and endure. On a cosmic scale, regions of space must have sufficient heavy elements, carbon, oxygen, nitrogen, and others synthesized in the hearts of stars and dispersed by supernovae, to build complex molecules necessary for biochemistry. This means that corners of the universe too close to its birth or distant from star-forming regions may lack the elemental richness needed for life. Galaxies themselves are subject to environmental factors. For instance, those with rampant starburst activity or active galactic nuclei may emit harmful radiation or disrupt delicate planetary systems. The galactic habitable zone concept arises from this, identifying regions within galaxies where conditions appear most conducive to stable planetary systems capable of sustaining life. Too close to a galactic center, the density of stars and resultant radiation is often too intense. Too far, metallicity may be insufficient. Within our Milky Way, this habitable zone hovers at an optimal sweet spot where stellar environments promote the development and preservation of life-bearing worlds. Zooming closer to individual stars, the stellar habitable zone, sometimes called our cosmic journey has traced the natural limits of observation defined by the universe's structure, physics, and evolution, culminating now in a pressing and profound question. Given all these cosmic boundaries, the speed of light, cosmic horizons, and accelerating expansion, do technological limits confine us ever more tightly? More intriguingly, is it conceivable that human or artificial ingenuity might one day surpass the cosmic horizon, breaking through what currently appears as an immutable limit to exploration and understanding? At its core, the cosmic horizon is dictated by fundamental physics. The speed of light, the finite age of the universe, and the expansion of space collectively set an ultimate observational perimeter. Beyond this horizon, regions remain causally disconnected. No signals, matter, or influence from there can reach observers here, now, or ever in the future. This presents a daunting constraint that technology alone cannot simply overcome by ordinary means. However, human history is replete with examples of transcending previously thought insurmountable frontiers by developing new technologies and perspectives. Could advanced propulsion systems, warp drives, or exotic energy sources someday allow us to physically cross or breach the cosmic horizon? Current physical understanding suggests not. Since the horizon arises from space-time expansion itself, even traveling at light speed would leave us unable to reach regions receding faster than light due to universal expansion. Concepts like warp drives or wormholes, featured in speculative physics and science fiction, remain theoretical conjectures without experimental support, and might themselves confront fundamental energy and causality constraints. On the observational front, technologies continually push the boundaries, detecting increasingly faint and distant signals. Telescopes utilizing multiple wavelengths, gravitational wave observatories probing ripples in space-time, and neutrino detectors expanding messenger channels widen our effective cosmic window. Yet these tools remain confined by the causal structure of the universe. Messages must still travel below or at light speed along expanding space, ultimately bounded by the cosmic horizon. Moreover, proposals for radical methods, such as quantum entanglement or novel physics, allowing faster-than-light information transfer, have yet to produce viable mechanisms that would enable surmounting cosmic horizons. Quantum entanglement, though exhibiting intriguing non-local correlations, does not permit faster-than-light communication due to fundamental constraints, preserving causality. There is also the speculative terrain of computational or simulation models mimicking universes or extracting information indirectly about beyond-horizon regions. But these approaches do not genuinely extend empirical observation. Instead, they rely on assumptions, models, or metaphysical perspectives beyond conventional physics. Thus, while technological progress expands our reach and capacity to understand the cosmos, current physics firmly guards the cosmic horizon as an absolute barrier. Our innovations can enhance precision and depth within the accessible universe, but cannot grant access to realms beyond causal connectivity. Nevertheless, the pursuit of surpassing cosmic limits drives scientific inquiry itself. Investigating the boundaries inspires deeper theories, perhaps revealing new physics, exotic particles, or profound connections between information, space-time, and gravity. Striving to comprehend and possibly transcend these cosmic edges shapes future avenues of research, like exploring quantum gravity, space-time topology, and even multiverse frameworks. In summary, technological limits intertwine with physical laws to enshrine the cosmic horizon as a fundamental boundary, not just of distance or time, but of possible causation and observation. For now, crossing this horizon remains beyond reach, but the quest to understand why motivates the enduring human spirit to seek, imagine, and expand the known. Our journey forward naturally intertwines the cosmic limitations dictated by physics and technology with profound philosophical questions about reality itself. Questions that guide the next steps in this overarching exploration. As we traverse the profound cosmic boundaries defined by physics, observation, and philosophical inquiry, we arrive at a provocative and increasingly influential idea that challenges conventional notions of reality itself. The simulation theory. This concept proposes that the universe we inhabit, with all its vastness and complexity, might not be the fundamental reality, but rather a computation, a simulated environment generated by some higher-order entity or system. If this is true, it imposes a new kind of ultimate limit, not of physics, but of computation, on what can be known, perceived, and even exists. Exploring simulation theory as a cosmic limit invites us to reconsider what reality means, how information and physics intertwine, and whether the ultimate cosmos is bounded by computational constraints. The essence of simulation theory gained mainstream philosophical traction with thinkers like Nick Bostrom, who formulated the simulation argument in the early 2000s. The argument suggests that one of the following propositions is very likely true. Civilizations either never reach the technological maturity to run high-fidelity simulations of conscious beings. They reach such capability, but choose not to. Or we ourselves almost certainly live inside such a simulation. Though speculative, this argument forces a fundamental exploration of the limits imposed by computation and intelligence. From a scientific and theoretical perspective, simulating a universe, even one as vast and intricate as ours, requires enormous computational resources. Any computational system has limits in speed, memory, and processing power. If our universe is a simulation, these constraints could manifest as subtle signatures or constraints observed in physical laws, constants, or phenomena, like discrete space-time granularity resembling a computational grid. Some researchers have explored whether quantum mechanics' probabilistic nature and apparent indeterminism could be features of a computational substrate. In this light, the universe's ultimate limits, such as the speed of light, the Planck scale, and the cosmic horizons, could be seen as artifacts of underlying computational rules, analogous to the rules governing a video game environment. They would define the simulation's resolution, update rates, and maximal causal reach, effectively bounding what the simulated inhabitants can observe and interact with. Moreover, information theory and entropy take on a critical role in simulation theory. The finite capacity to store and process information in the hypothetical computational hardware might restrict the complexity and scale of the simulated universe, introducing constraints on observability and state evolution. These limits could parallel those discovered in black hole thermodynamics and holographic principles, suggesting deep connections between gravity, information, and computation. Philosophically, simulation theory disrupts traditional metaphysical assumptions. If reality is a computation, questions about the real universe behind the simulation arise, as do issues about the nature of consciousness and free will within simulated contexts. It also raises the possibility that some cosmic limits we perceive are not fundamental, but imposed by the design or architecture of the simulation. Critically, while simulation theory is intriguing, it currently lacks empirical confirmation. Proposed tests, such as searching for quantization patterns or anomalies in cosmic rays, have yet to yield definitive evidence. Nevertheless, the hypothesis motivates interdisciplinary research, bridging cosmology, computer science, information theory, and philosophy. In contemplating simulation theory, we embrace an ultimate cosmic limit that transcends physics alone. The possibility that all we observe is bounded by computational constraints and design choices external to our universe. This profound perspective opens new avenues for understanding the cosmos, information, and existence, reminding us that cosmic limits may be as much about the nature of reality as about the boundaries of knowledge. From here, our journey naturally flows into deeper philosophical terrain, examining whether the universe can ever be fully understood and the intrinsic limits of human cognition and science, a compelling topic we explore next. As our journey through the cosmic expanse and its many physical and conceptual boundaries draws us toward deeper reflection, we confront one of the most profound questions that have captivated thinkers for centuries. Can the universe ever be fully understood? Beyond the empirical confines of observation and the theoretical limits imposed by physics lie philosophical considerations that challenge the very scope of human knowledge, cognition, and understanding. This section explores these philosophical limits and the nuanced nature of ultimate comprehension in the face of a vast, complex, and perhaps inherently unknowable cosmos. The aspiration to completely understand the universe, its origins, laws, structure, and fate, has propelled science forward since antiquity. Yet, as our knowledge deepens, so too does the awareness of formidable obstacles. First and foremost is the recognition that human cognition itself is bound by biological, neurological, and conceptual constraints. The brain, remarkable as it is, evolved to navigate terrestrial environments, not necessarily to grasp the totality of the cosmos. Cognitive limitations, biases, and the finite nature of human lifespan impose natural boundaries on our capacity for comprehension. Moreover, the nature of scientific inquiry is intrinsically provisional. Scientific theories and models seek to approximate reality through observation, testing, and refinement, but must always remain open to revision in the light of new evidence or perspectives. This humility introduces an epistemological limit. Ultimate knowledge might forever elude us, replaced by ever-improving, yet incomplete, descriptions. The quest is asymptotic, approaching truth without necessarily attaining perfect or final understanding. Philosophical perspectives such as epistemological realism suggest that a reality exists independently of our perceptions and that, in principle, it could be fully apprehended. However, other schools, including forms of instrumentalism or pragmatism, emphasize that our knowledge is essentially a useful construct rather than an absolute depiction. These viewpoints highlight that understanding might be inherently contextual, shaped by the frameworks, languages, and methodologies available to humans. The limits epitomized by Gödel's incompleteness, theorems in mathematics underscore that within any sufficiently complex formal system, certain truths cannot be proven using the system's own rules. By analogy, it remains an open question whether our physical theories and conceptual frameworks will ultimately prove incapable of fully describing the universe's deepest structures or dynamics. Quantum mechanics further complicates the notion of absolute understanding. Its probabilistic nature and the observer effect introduce fundamental uncertainties, limits to precision and prediction, that are not technical but intrinsic. Similarly, the limitations imposed by cosmic horizons, entropy, and information bounds discussed previously constrain the accessible knowledge of the universe as a whole. Certain philosophical traditions speculate that the universe may possess facets forever beyond human grasp, whether due to intrinsic complexity, infinite regress, or the presence of metaphysical elements inaccessible to empirical methods. In this view, some cosmic mysteries, including the ultimate origin of physical laws or the nature of consciousness, might remain eternally enigmatic. Despite these profound limits, the human capacity for creativity, collaboration, and technological innovation continues to expand the frontiers of knowledge. Scientific revolutions, from Newtonian mechanics to quantum field theory and cosmology, demonstrate that understanding can grow in unforeseeable ways, transcending previous horizons. Ultimately, the contemplation of philosophical limits cultivates a nuanced attitude, embracing both intellectual humility and enduring curiosity. It acknowledges that while absolute or final understanding may remain beyond reach, the journey of inquiry is itself a valuable and perhaps infinite pursuit. As we shift from these reflections to examining the ultimate fate of the universe, questions about cosmic limits naturally converge with those about time, entropy, and the destiny awaiting all realms of existence, fusing philosophical contemplation with physical reality in the grand finale of cosmic exploration. As we reach the culmination of our cosmic journey through the limits of observation, physics, and philosophy, we confront one of the most profound questions about the cosmos: its ultimate fate. What lies ahead for the universe in the far distant future? Will it expand forever into a cold, desolate void, collapse back upon itself in a fiery crunch, or follow some other exotic destiny? Exploring these scenarios requires integrating our understanding of cosmic expansion, matter, and energy content, dark energy, and thermodynamics, all of which together frame the universe's long-term evolution and the ultimate limits that define its fate. The traditional broad categories for the universe's destiny include the heat death, the Big Crunch, and more speculative outcomes such as the Big Rip, or cyclic models of rebirth. Each scenario is governed by the interplay of gravity, expansion, and the mysterious components of dark matter and dark energy. Heat death describes a universe that expands forever, gradually exhausting all usable energy. As expansion accelerates, powered by dark energy, galaxies recede beyond each other's horizons, stars turn off after exhausting their fuel, and matter decays or becomes locked in inert remnants. The cosmos steadily approaches thermodynamic equilibrium, a state of maximum entropy in which no energy gradients remain to sustain processes like life or work. This bleak but stable state of cosmic cold and darkness would mark the universe's functional end, a slow fade into silence over unimaginably long timescales. The Big Crunch, once considered the natural counterpart to expansion, envisions a universe where gravitational attraction eventually overcomes expansion. The cosmos reverses course and contracts, compressing matter and energy back toward a hot, dense state. This contraction culminates in a singularity, a reversal of the Big Bang, potentially setting the stage for a cosmic rebirth or a cosmic cycle. However, current observations indicating the accelerated expansion of the universe make this scenario unlikely under the simplest models. More exotic is the Big Rip scenario, in which dark energy's repulsive force grows stronger over time, eventually overcoming all binding forces, from galaxies to atoms. The fabric of space-time itself would tear apart, obliterating all matter and even space-time structure in a finite future. Such a dramatic end would impose a final absolute cosmic limit, where all known physical structures dissolve. Alternative models propose cyclic universes, where expansion and contraction repeat indefinitely, or the universe transitions into different phases or dimensions. These hypotheses remain speculative, but highlight the diversity of thought about cosmic fate. Underlying these futures are deep physical laws relating to entropy and information. As the universe evolves, increasing entropy constrains the form and complexity that can exist, linking the ultimate fate to fundamental limits on knowledge and existence. Importantly, our understanding of cosmic destiny continues to evolve with observations and theoretical advancements. The discovery of dark energy dramatically reshaped expectations, underlining that cosmic fate hinges on the nature of components we are still striving to understand. Ultimately, contemplating the universe's end confronts us with the humbling limits of human knowledge and the vast scales of cosmic change. It is a profound meditation on impermanence, destiny, and the boundaries of existence itself. As we next consider transcending limits through thought experiments and speculation, we embrace the spirit of inquiry that propels us toward understanding, even in the face of the universe's vast and mysterious boundaries. As we stand at the nexus of cosmic understanding and boundless curiosity, we arrive at a realm where the mind ventures beyond empirical constraints, transcending limits through thought experiments and bold speculations. This domain lies at the frontier where physics meets philosophy, imagination intersects with rigorous logic, and where probing the unknown often requires envisioning realities that stretch or even break established principles. In this section, we explore how contemplating abstract scenarios, paradoxes, and theoretical possibilities expands our grasp of the universe's ultimate limits and inspires new paths of inquiry. Thought experiments have long served as invaluable tools in physics. Pioneers like Einstein used them to challenge prevailing notions and reveal hidden consequences of physical laws. Consider the famous elevator and train paradoxes illustrating general relativity's subtleties. In cosmology, thought experiments push us to consider extreme conditions. What happens near singularities, across horizons, or in universes with different physical constants? These conceptual probes illuminate potential boundaries where known physics might yield or require extension. One profound speculation is the nature of information and reality itself. The holographic principle, first inspired by black hole thermodynamics, suggests that all information contained within a volume can be described by information on its boundary surface. This challenges the traditional view of three-dimensional space, hinting at a universe perhaps fundamentally encoded on lower-dimensional structures. Contemplating this principle leads to revolutionary ideas about the fabric of spacetime and the limits of information storage and processing, with far-reaching implications for physics and cosmology. Another fertile ground for speculation lies in the idea of multiverses, vast ensembles of universes with varying laws, constants, or structures. The inflationary universe framework and string theory landscapes naturally predict such multiverses. Imagining their properties extends the cosmic limit from a single universe to an infinity or vast plurality of realities, each with its own observational boundaries. While inherently challenging to test, these concepts stimulate creative thinking about physical law, the anthropic principle, and the nature of existence. Quantum mechanics itself presents paradoxes like Schrödinger's cat and the measurement problem, questioning the precise nature of reality and observation. Interpretations such as the many worlds hypothesis speculate that every quantum event spawns branching realities, creating a complex, layered cosmos of parallel histories. These ideas pose limits not only to what can be observed, but to what it means to be real, compelling us toward new philosophical and scientific vistas. Speculations about time travel, faster-than-light communication, and exotic space-time geometries like wormholes test the boundaries of causality and relativity. Thought experiments exploring closed time-like curves or hypothetical warp drives probe whether nature's limits can be bent or if fundamental principles always safeguard cosmic order. Further speculative scenarios consider whether consciousness or life could transcend physical limits, invoking ideas such as panspermia, cosmic seeding, or even the transference of minds into artificial substrates, concepts that interlace astrophysics, biology, and technology in the context of cosmic boundaries. Throughout these ventures, the interplay between rigorous mathematics, empirical evidence, and imaginative exploration guides progress. Although many speculations remain beyond current verification, they kindle curiosity, drive theoretical innovation, and refine experimental designs to edge closer to reality's deepest truths. In embracing these thought experiments and speculations, we acknowledge that transcending cosmic limits often means confronting the unknown with humility, openness, and creativity. They remind us that the universe's boundaries are not merely barriers, but invitations. To question, to imagine, and to expand the horizons of human understanding. From here, our journey leads naturally to reflect on the human perspective itself, our cosmic place, how we measure and interpret the universe, and how these ultimate limits shape our view of reality and our role within it. As we step back from the grand cosmic scales, horizons, and ultimate limits, it becomes essential to center our reflection on the human perspective, the unique vantage point from which we measure, interpret, and understand the universe. Our place in the cosmos is not simply a geographic or spatial position, but a confluence of scientific inquiry, observational capacity, and existential awareness. Grasping how humans situate themselves in this vast cosmic context illuminates not only the methods by which we measure the universe, but also how we conceptualize our role within the boundless expanse. From an astronomical standpoint, Earth occupies a seemingly ordinary position, a modest planet orbiting a common star in the sprawling disk of the Milky Way galaxy. Yet this ordinary locale belies the extraordinary journey humanity has undertaken to decipher the cosmos. Through centuries of observation, mathematical reasoning, and technological innovation, humans have transcended the limitations of unaided senses to map the universe, from nearby planets to galaxies billions of light-years away. Measuring the cosmos involves a hierarchy of methods known as the cosmic distance ladder. It begins with direct approaches like parallax, leveraging Earth's orbit to triangulate distances to nearby stars. From there, astronomers employ standard candles, objects with known intrinsic luminosity, such as Cepheid variables and type Ia supernovae, to estimate distances outward. Redshift measurements enable inference of the universe's expansion and the distances to even more remote galaxies. Each rung of this ladder builds on well-characterized physics and increasingly sophisticated instrumentation, enabling us to extend our vision ever further. Yet these methods are intricately tied to our embedded perspective in spacetime. Observations are bounded by light speed and cosmic horizons, meaning all knowledge is inherently observationally constrained. Our reference frame is Earth-centered only in a practical sense. Cosmologically, no privileged center exists, as the universe expands uniformly everywhere. This Copernican principle informs how data are interpreted, ensuring that no point in space is assumed special unless proven observationally. Furthermore, human cosmology blends empirical measurements with theoretical modeling. Data gleaned from telescopes and detectors feed into computational simulations and theoretical frameworks such as general relativity and quantum field theory. This interplay defines not only what can be measured, but how measurements are understood in a consistent cosmological narrative. Beyond the technical, the human perspective embraces philosophical contemplation. Questions arise concerning the significance of our observational limits, the arrow of time, and the nature of consciousness itself. We ponder whether understanding the cosmos reveals ultimate truths or merely constructs effective models shaped by human cognition and language. Our measurements of fundamental constants, like the speed of light, gravitational constant, or Planck's constant, illustrate the interdependence of human experience and universal parameters. Through refined experiments on Earth and in space, we continually improve these measurements, shrinking uncertainties and refining cosmological parameters such as the universe's age, composition, and geometry. Additionally, technology shapes the human perspective profoundly. From the pioneering telescopes of Galileo to the Hubble Space Telescope, and now to next-generation observatories like the James Webb Space Telescope and gravitational wave detectors, our ability to probe the cosmos expands, illustrating an ever-deepening dialogue between curiosity and capacity. Recognizing our cosmic place is also a humbling reminder of scale and impermanence. Earth is but a pale blue dot amid immense distances. Human history occupies an infinitesimal fraction of cosmic time. Yet within this small window arises consciousness capable of contemplating the universe's entirety, a testament to the remarkable intersection of biology, physics, and chance. Ultimately, the human perspective serves as both anchor and compass in the grand cosmic voyage. It shapes how we define the observable universe and its boundaries, how we interpret the stories carried by distant photons, and how we situate ourselves in an ever-evolving cosmic landscape. With this perspective in hand, our exploration logically leads to revisiting the cosmic limits themselves, reflecting on what remains unanswered, the mysteries that continue to inspire, and the horizons that beckon discovery. In doing so, we embrace the ongoing dialogue between humanity and the cosmos, a dialogue as boundless as the universe itself. As we conclude this expansive exploration of cosmic limits, it is fitting to reflect on the vast terrain we have traversed, and, more importantly, to consider what profound mysteries and unanswered questions continue to challenge our understanding of the universe. Throughout our journey, we've confronted the boundaries imposed by the observable universe, cosmic horizons, the finiteness of the speed of light, the enigmatic forces of dark energy, the intricate dance of information and entropy, and even the philosophical and speculative ideas that stretch our imagination. Yet for all our advances, the cosmos still holds deep secrets beyond our present grasp. One fundamental open question centers on the true nature of dark energy. While observations firmly establish that it drives the accelerated expansion of the universe, its origin and fundamental properties remain elusive. Is dark energy a cosmological constant, an intrinsic vacuum, energy permeating space, or a dynamic, evolving field? Could it be a signal pointing us toward new physics beyond the standard model and general relativity? Resolving this mystery could redefine our cosmic horizons, fate, and the limits of observation itself. Similarly, the quest for a complete theory of quantum gravity persists. The Big Bang singularity, the Planck scale, and black hole interiors challenge our current frameworks, beckoning a unified understanding that coherently merges quantum mechanics and gravitation. Such a theory might resolve classical singularities, illuminate pre-inflationary conditions, and redefine cosmic boundaries. The multiverse hypothesis prompts profound questions about the very nature of reality and observability. If countless universes exist beyond our horizon, what defines the limits of scientific inference? And can we ever test or hope to detect their presence? The tension between empirical testability and theoretical elegance remains an open frontier. Philosophically, the limits on knowledge and observation provoke reflection on cognition's finitude, the role of consciousness, and whether the universe is comprehensible in its entirety or eternally veiled in mystery. The implications extend to the meaning of existence and humanity's place as observers within a grand cosmic stage. Technologically, while we continue to extend our reach with ever more sensitive instruments and innovative methods, the cosmic horizons and fundamental speed limits inevitably constrain our access. Whether breakthroughs, currently speculative technologies, or new physics might someday allow surpassing these frontiers is unknown, but remains an inspiring pursuit. Lastly, the ultimate fate of the universe, be it heat death, big crunch, rip, or something unforeseen, remains a subject of active research. Determining which path the cosmos will follow requires deeper insights into fundamental physics, dark energy's nature, and the interplay of matter and space-time. In embracing these unanswered questions, we acknowledge that cosmic limits are not mere endpoints, but invitations to explore, to question, and to wonder endlessly. They remind us that the universe is a living mystery, and our quest for understanding, though bounded, is infinite in spirit. As we close this comprehensive reflection, we stand humbled and invigorated, aware that every limit we encounter is but a threshold to new discovery, a testament to the enduring human desire to comprehend the ultimate cosmic frontier.